Hey, pre-calc students, this is Hyperbola's day 1. It is the last conic section of our 4. We've learned circles, we've learned parabolas, we've learned ellipses. This is the grand finale here. We're going to be talking about the properties and graphs of hyperbolas today. This first image in the notes might look a little intimidating. There is a lot going on in this diagram. The good news is that it does have some similarities to that of an ellipse. The actual hyperbola in this sketch are these curves right here with the arrows at the end. So what we're going to do really just on this front page of the notes is highlight how do we get the graph based on the equation, and then we'll kind of go and build from there. So the first thing we have to know is that A is still the distance from the center to the vertex. And in this diagram right here, the vertex or the vertices of this hyperbola would be here and here, and you can see those distances represented by A0 and negative A0. The center of this hyperbola happens to be at the origin to get started. We'll branch away from that, of course, but that's how we get to the vertices. They're A away, and we'll look at the equations in a moment and see how we get A. So what is B then? B used to be center to the end of the minor axis for an ellipse. Now B is representative of center to what's called the end of the conjugate axis. So we have these points that I will still label as B and B prime. You can kind of see them up here in the graph. Here would be B and B prime, something like that. And I will do my best not to goof up and say minor axis when it relates to a hyperbola. The fact of the matter is that A is not the largest value anymore. Sometimes it's bigger than B, but it doesn't have to be bigger than B. So if B is larger, we can't really define B to be the minor axis anymore. For a hyperbola, it has the special name of the conjugate axis. What does C represent? C is still center to focus. That's what it was for an ellipse. We'll talk about how we're going to determine the value of C. A little bit different than how we determine it for an ellipse. So you can see these points right here. We've got F and then F prime. So just like we had, like I said, for the ellipse, from the center to here is a length of C. Notice how C is bigger than the value of A. And what I want you to sort of think about is that the hyperbola will eat the focus, just like the parabola used to like to eat the focus. The hyperbola branches here, these curves, are going to open up and eat those foci, kind of like two little Pac-Mans. Okay, what is some other key info that is critical to know about a hyperbola? We have 2A and 2B. They used to be the major and minor axes. Now they are the lengths of the transverse and conjugate axes. Conjugate axis, I use that term up here. Transverse will be a new term for us. We probably don't use it a ton until we start working backwards, right? We didn't really talk about major axis when we sketched a lot. We primarily used that term when we were working backwards, given some information about that conic section, coming up with the equation. What else do we have to know? We have to know the relationship between A, B, and C has changed, like I showed you in the diagram. The distance from the center to the focus, C, was bigger than the other values. So C squared now equals A squared plus B squared. There is still that Pythagorean relationship, which is good news. Okay? So we've got that taken care of. The length of the LR, more good news. 2B squared over A. That's exactly what it was for an ellipse. So the graph looks super different, but there are going to be a lot of similarities, which also include the equations. I know that these are printed on the sheet, but these should look almost identical to what the standard form equations of an ellipse looked like. So if I were to ask you what is the only difference between the equation of a hyperbola and the equation of an ellipse, I'm hoping you would identify it's really just that sign in between. If I change this right now to a plus, it is now the equation of an ellipse. So just having that one little minus sign in there completely changes the graph to make it look like this. That's the graph that you're seeing up at the top of the page, but it doesn't have to look like that. It could open up and down vertically. I've had students tell me the way they remember this is first of all, the way I remember is just that if y squared is positive, and I always list the positive term first. So if the y's are squared first, then it's going to open up vertically, and students have told me y to the sky. I don't know if that helps you. Y to the sky means that if y squared is first, you're going to open up and down. X squared's first, it's going to open left and right. Okay. Now that we hopefully have a better sense of horizontal versus vertical, we're going to graph one of each type, I'm sure, at some point today. The last somewhat challenging piece, because it's a new piece of information for hyperbolas, would be the equations of the asymptotes. So what do I mean by those? If you come back to the sketch up here, we have these dotted lines. The dotted lines are important because they help me determine how wide these branches, we call them, of the hyperbola should open. Because otherwise, should it have opened like, can you see my hand now? Should the hyperbola open like this or should it open like this, right? We can't tell that until we sketch in these dotted lines. I will show you an easy way to make those dotted lines when we go to make our sketch. You can see kind of this box that we're using as a guideline there to get these lines potentially. But I'm kind of curious as to know, like, well, what are the equations of those lines that the graph is approaching? And the easiest way to think about it is that how do I get from the center to this point right here? Well, it's a rise over a run. What am I rising? I'm rising B, and then I'm running A, because that's this distance down here. So the slope of a horizontally opening hyperbola is up B over A. Oh, and by the way, this line over here has a slope of down B over A. So one has a positive B over A slope, the other has the negative B over A slope, which is why we have that as the slopes of those asymptotes. If it was a vertical hyperbola, it would just be the reciprocal of that, up A and over B. Now, I'm not just going to ask you for the slopes of the asymptotes, I'm going to ask you for the equations of these lines. So if we know the slope and we know what point they go through, because by the way, they have to go through the center of the hyperbola, the center HK. Here's what those equations are going to look like. I know it looks like a lot, but all this is that point slope form that we learned at the very beginning of the matrices unit, which feels like a long time ago now. But we've seen this form before. This is just the equation of a line that contains the point H comma K and has either the slope B over A or the slope A over B. All right, a lot of info here. It's going to start to make a lot more sense once we piece it together and start making some graphs of hyperbola. So let's jump right into that. For number one, we have the hyperbola x squared over 9 minus y squared over 16 is equal to 1. Okay, so here's some important things that we're going to look at. We won't always graph today a center at the origin, but this one does have a center at 0, 0. And the values of A and B, it's important to note that A squared is always first. It doesn't have to be largest. If this was a plus sign to make it into an ellipse, we would have said A squared is 16 because we are so used to saying, oh yeah, A is the bigger number. But if I look at this, I know that according to those two standard forms that we just looked at a second ago, that A was always in the first denominator, no matter what. So I know that A is 3 and B is 4. It's a little bit tough for us to get used to that because we're so used to A being the largest, not necessarily true anymore. What else do I know about this hyperbola? I know that because x squared comes first, or that x squared is the positive term, that it's going to be opening horizontally. Just like the image on the front page is going to open up its branches to the left and to the right. Before we make our sketch, we typically also might find the value of C. Remember, the new relationship is that C squared equals A squared plus B squared. So in this case, C squared would equal 9 plus 16, which is 25. So that's going to give you a value of C, which is equal to 5. We're very used to C not necessarily being a nice value. So in this case, it is, which is nice, but it doesn't have to be. Let's start plotting here. Okay. Center 0, 0. The value of A gets me to the vertices. The vertices are these points right here. So because it's opening up horizontally, you have to go to the right 3 and to the left 3. Doesn't really matter what you call V and V prime. Okay, label those. The value of B gets you the up and down distance then. These are called the ends of the conjugate axis. So you've got B up here and B prime down there. Okay. Once you plot those points, do not make an ellipse. It's very tempting. What you're going to do is you're going to make a box that connects those 4 points. So start at any of them. I'm going to start at V over here. I'm going to go up until I get up to the height of B, go across, come down through V prime. Hopefully you guys can see this okay. Okay, so I'm making this red dotted box. I like to make it dotted because it's really not an official part of the sketch, right? It's not a part of the graph of the hyperbola branch, but it is something that helps me form that. What we also saw on the front is we have these asymptotes that are pretty important so that I know how wide should I curl this hyperbola around. How do I draw the asymptotes? They're the diagonals of this rectangle. So just try and carefully make sure that when you draw on the diagonals, that you go through the corners of the rectangle. Okay. It's just an approximation. It doesn't have to be perfect. But I want to see that you've at least made an attempt here. And once you've drawn those in, now you are ready to draw your hyperbola that opens up to the right and opens up to the left. Please make sure it connects to V and to V prime. So there's the hyperbola. While I'm at it, I probably should also use my value of C to get to the foci. So if I go here, that's 5 units out. This would be 5 units to the right of the center. And there's F and F prime. Okay. Now that we have that established, of course, what we need to do is list the important coordinates that we've sketched here. So here we go, the vertices. How did I get to them? I went left and right 3. So those were at plus or minus 3, comma 0. Now, if the center is something other than 0, 0, we know that these might start to look a little bit different. Okay, so B and B prime went up and down 4. So that's 0 plus or minus 4. Going a little fast through some of this initial info, but F and F prime would be at plus or minus 5, comma 0. Okay, then we need the length of the LR. Same thing as what it was before. I haven't even shown you the LR yet. I forgot to show you that on the front page, but I'll show you that in a second. The last rectum would be 2b squared, so that's 2 times 16 over a, which is 3. So the LR has a length of 32/3. So how do I get to the ends of the LR? Where are they even located? Well, the LR is those segments that go through the foci. Okay. So we've got an endpoint here and here. And then we've got endpoints here and there. Okay. Now those in theory should be the same size. One looks a little bit bigger on my sketch than the other, but they should each have a length of about 32/3. How do I get to those endpoints? If this whole thing has a length of 32/3 from the focus, we have to go up 16/3 and we have to go down 16/3. So from that focus, from that plus or minus 5 location, you have to go up and down plus or minus half the length of the LR. This is a process that looks familiar to us because it's the same idea as what we did with the ellipse. Same type of idea. All right, as what we've seen with the ellipse, I don't usually write all these numbers in here. It's just to help you get started. Last but not least, asymptotes. If you don't want to memorize that equation that we saw on the front page of the notes, simply look at your sketch. What do we know? We know that the lines go through 0, 0, the center. And we know that they have a slope of up B and over A, right? Or down B and over A. So the equations will be y equals plus or minus that ratio of B over A, which is 4/3 x. If the center was anywhere else, if it got shifted to, let's say, the point 1, 2, over here we'd say x minus 1, over here we'd say y minus 2. It's just a way to make sure that we're including the center value there. This looks a little bit simpler than what we saw on the front page of the notes because the center is at the origin, okay? All right, asymptotes take a little while to get used to. You'll get there. All right, then we get to example 2. We're like, oh man, what's this? The 1764, I don't know, something probably historical happened in 1764 that I don't remember. But I'm going to divide both sides by 1764 to get started. And just to double check, I'm pretty sure 36 times 49 is that value because we've seen that happen a lot, but I probably should double check it. 36 times 49 is, what do we know? 1764. So we're good. All right, so what that means is when you divide both sides there, you're going to get y squared over 49 minus x squared over 36 is equal to 1. So one little step, and we're into standard form. All right, what do we know about this hyperbola? We should know that the center is again at the origin. We should know that the value of a is 7, not because it's biggest, but because it's always first. B is 6. Since y squared comes first, and y squared is positive, this is going to open vertically this time. So we're going to see a hyperbola who opens up and down. If c squared equals a squared plus b squared, we're going to have c squared equals 49 plus 36, which sounds like 85. I should probably double check it. Yeah, that sounds good. 85, so square roots. C equals the square root of 85, which is approximately square root 85 is about 9.2. So we'll use that when we plot the foci. But as always, when we list the coordinates, we're going to go ahead and use radical 85 when we do that. Okay, these are 10 by 10 grids, by the way. That's going to help me to make my work a little bit more efficient. So if it's opening up and down, those vertices right here are going to be 7 units up and down. So rather than counting up 7, I'm just going to count back 3. There's one vertex. Here's another vertex. V prime. We've got to go 6 to the left and right. So you can count 4 back if you want, if that makes your job a little bit easier. There's B and B prime. Okay, we need a box that goes and connects those 4 points. Here we go. Okay, so create that rectangle that contains V prime, B prime. Once you have that sketched, go ahead and draw. Remember, I have to go through the center. Draw the diagonals of the box, which go through 0, 0 in this example. Here they are. Okay, and just make sure that this time, instead of opening up left and right like we saw in the first one, because the y squared was first, we're going to open up, we're going to open down. Okay. We know where the foci are located. They're 9.2 away. 9.2 is pretty close to that top and pretty close to the bottom here, right? Just a little bit more than, and it doesn't have to be perfection, of course. You know, we're just looking that it's in the right general location. So somewhere between 9 and 10. All right, that was a fast sketch, but I think if you're following along here, hopefully you're ready to start listing some coordinates with me. What do we have? We need the vertices. All right, let me set this up here. Okay, so we've got vertices V and V prime. Went up and down this time, so it's 0 plus or minus 7. Ends of the conjugate axis went left and right 6, plus or minus 6, 0. F and F prime went up and down the square root of 85. Okay, just try and be consistent. Don't use the 9.2 value. The LR has a length of 2b squared over a. So b squared is 36, and a is 7. That's going to be 72 sevenths, which gets you the ends of the LR. Okay, this time the LR segments are horizontal like this. I know you probably can't see this right now, but I'm drawing a same segment up there. There it is. All right, so how do I get there? Well, I have to go left and right from the focus, half of this distance. So it's going to be plus or minus 36 sevenths, and then plus or minus the square root of 85. Last thing is the asymptotes. The only difference this time is that the asymptotes, when I do the rise over the run, we're rising A and running B, okay? So make sure when you do the ratio for the slope, it's going to be A over B, which is 7 over 6 for this example. Y equals plus or minus 7/6 x. We're going to see how that changes a little bit in the next example because the center, we're moving away from the origin. Okay. Let's go ahead and take a look.